Thank you very much, Ben. Thank you. And good morning, everybody. Great to see you all taking part in Maths Week Ireland. This will actually be my, I think, third or maybe fourth Maths Week Ireland, but the first one I'm doing not as a university student, which is quite exciting. So I guess I've worked my way up now to be able to present to you all, which is pretty cool. So today, as Ben said, I'm going to talk to you about maths and sport. And we're going to look at two of my favorite sports. We're going to look at football and we're going to look at marathon long distance running. And we're going to use some mathematical techniques that you will have learned about at school. And we're going to apply them to hopefully new scenarios, seeing how we can model sports and try and understand sports from a mathematical perspective. So just a very quick intro to me. So I am Dr. Tom Crawford. I'm a mathematician at the University of Oxford over in England. And I also do lots of stuff online. So I have a YouTube channel, Tom Rocks Maths, and I also do quite a few videos with Numberphile. So if you have like a weird voice in your head saying, where have I seen this random person before? It may well be in YouTube videos. So today, we're going to start by talking about football. And I'm going to apologize. Always a good way to start a talk with an apology. I'm going to apologize for the big, let's say, Ireland football team, men's football team supporters out there, because I'm going to show you a video from the weekend. Not that you wanted reminding, but just to talk about penalty shootouts. So this is a clip from the Euro 2021 now, I guess, qualifying game, which took place at the weekend.
Well, Alan Brown must have been wondering how he didn't score in normal time after he came on from the bench. He has to score this. He just has to. Oh, and he hasn't! That just about sums up how the game itself went for Alan Brown, as he's denied, and Ireland blink first.
So again, my apologies, showing you Ireland missing a penalty and going on to actually lose that shootout against Slovakia, meaning that they unfortunately don't qualify for the European Championship. Now, the reason I'm showing you this is I'm here to help. We can all help as mathematicians because we can figure out and we can use maths to help us be better at taking penalty kicks. So whilst we're starting on a bit of a bum note, we're thinking positive, we're thinking optimistic. How can we make sure this doesn't happen again and that the Irish national team can qualify for the World Cup in 2022? But before we get to that, I thought it would be interesting to look at how certain countries compare with their penalty shootout records. So we've got here a bar chart. Don't worry too much if you can't read the numbers. It's in order of percentage of wins in penalty shootouts for the men's national football teams. So we've got England doing pretty bad down there with a 33% win ratio in penalty shootouts. We've got France, the current world champions, at 50%, which is perhaps what you would expect if it was completely random, win or lose, similar to a coin flip. And then we've got Portugal and Argentina, two teams that are traditionally quite good at penalty shootouts, and they obviously have a win percentage higher than 50, so they're both at 60%. So the first thing I want you to think about, and as Ben said, if you want to do a vote in your class and then type that in the chat so I can see the results, I want you to vote for which position do you think Ireland slot into on this chart. So as I say, this is increasing. So gap A is the Irish national team's win percentage in penalty shootouts, is it less than 33%? So are Ireland worse than England at penalties? Then vote for gap A. If you think they're between England and France, so between 33 and 50, then vote for gap B. If they're better than the world champions, but better than France, but not quite as good as Portugal and Argentina, that would be gap C. And if they're top three in the world, go for gap D. So if you want to I'll give you about 30 seconds, do a quick vote, maybe type your answers in the chat and let me know how you're all thinking. And then I will, of course, reveal the results. So again, this is looking at the win percentage or win ratio of the Irish men's national football team in penalty shootouts. So I've got one answer so far, which is saying A. So clearly not much confidence in the Irish team. We've got a B. Okay, so again, not too much confidence, but thinking maybe they beat England. And then another vote for B. Okay, it seems like I'm guessing A and B. So those of you who unfortunately can't vote or take part in the chat, maybe you were also thinking A and B. So the correct answer I can reveal is actually B. So Ireland also have a 33% win ratio in penalty shootouts. So they drop in there just sort of equal with England. And also I put in Italy as another comparison, because again, a traditionally very good country at football, but not great at penalty shootouts. So well done anyone who said B. Anyone who went for C and D, I think you're maybe being a bit too optimistic. So I think it's 1 win in 3 is the actual numbers that give you that 33% win record. Now, Gap A, the worst, well, not the official worst team in the world, the worst team out of the ones I selected. So I looked at traditional teams that win tournaments, shall we say, and I looked at teams that are highly ranked in the world rankings. So the worst would be the Netherlands, based on that sample. So they come in at 29%. So they are officially the worst of the big teams, shall we say, when it comes to penalty shootouts. The middle gap in C, we've got Brazil and Spain. Brazil at 54%, Spain at 56%. So both a little bit better than completely random. And then now top 3. So does anyone have, of the schools, do any of you have any ideas or want to put any guesses for countries that are going to come in the top 3? So which countries have you seen win lots of penalty shootouts, or traditionally do you think of? Oh, straight away, we've got 2 Germanys in there. We've got is that a Poland? Interesting shout. We've also got an Italy. Italy are down here already. Whoever said Italy, but we got 2 Germanys there, and I knew Germany would come up first because Germany are known as being really good. They're really efficient at taking penalties. They just don't miss. So Germany, yeah, very good. Come in second place here. So they have an 86% win ratio. They've won 6 out of 7 penalty shootouts. I was going to guess at Nigeria. Nice guess. The other 2 haven't come up yet. The other 2 are European countries. So we've got Belgium coming in at 100%. Belgium have only been in, I think they've only been in 1 penalty shootout though. So it's maybe skewing the data a little bit. But Belgium have been in 1 penalty shootout, which they won. So they do come in with a 100% win record. And then in third place, we've actually got I think someone's just typed it, Croatia. Very well done. So I was about to say that the losing World Cup finalists from 2018. So Croatia come in at 67%. So they've won 2 out of 3. Both of those, in fact, were at the last World Cup. So until recently, Croatia weren't very good at penalty shootouts. So now they've turned it around. So again, Ireland, much like England, not great at penalties. So again, as we saw at the beginning, how can we use maths? How can we help the Irish team to be better at taking penalty kicks? And even how can we help anyone watching who plays football? How can we help you to be better at taking penalties using maths? So the first idea that we're going to talk about is something called the unsavable zone. So here we've got a diagram of a goal. So obviously the black rectangle is your net. And then we've got the little goalie diving and the ball. And then we have this thing labeled, this red line, which I've labeled here as the diving envelope. Now, this is calculated in 2 ways. So first of all, an experiment was done by Ken Bray at Bath University. So this is real research done by a mathematician, which was looking at how far can a goalkeeper dive in the time between the ball is kicked and the ball going into the net. So on average, when you take your penalty from 12 yards from the goal, you have around 0.5 seconds, so half a second between the ball leaving the foot of the striker or the player and going into crossing the goal line. So the experiment you can do, or the question you can ask, is to say, as a human being, with the limitations of being a human. How far can you actually move or dive in half a second? And you can, of course, conduct experiments, which is exactly what they've done. So using a special slow motion camera to make sure that the goalkeeper doesn't dive early or anything else. And then you can also measure how far can a goalkeeper dive in half a second. And using data from several different goalkeepers, professional and amateur, the average distance that you can reach as a human in half a second is this red line. So this is starting from the center of the goal. So that would be like the first assumption in our model. Of course, you don't have to start in the center of a goal, which is why some goalkeepers will save shots maybe down here or maybe down here, because they're either diving early or they don't start in the center of the goal. But as trying to get a general picture, starting in the middle of the goal, only moving when the ball has been kicked, in half a second, a goalkeeper can reach the red line. So when you're now the penalty taker, that suggests to maximize your chance of scoring, put it where the goalkeeper cannot reach. Because then, of course, the goalkeeper can still save it, perhaps, but they would have to dive early or they would have to not start in the center of the goal. But if they do start in the middle, if you put the ball outside of this red line, it's a very, very difficult save for the goalkeeper to make. So that's our first tip. And we call this the unsavable zone. Outside of the red, but inside of the posts, inside of the goal, these two areas are called the unsavable zone. Now, the data for penalties also support this. So again, over at Bath with Ken Bray, so they looked at hours upon hours of footage of penalties being taken. And they included penalties that were scored, penalties that were saved by the goalkeeper, and even penalties that missed the target altogether. And then for each of those penalties, you can draw a cross for where the shot went in the goal. And of course, again, including ones away from the goal. And then you can say, right, which ones were scored, were successful, and which ones weren't, which ones were misses. And based on all of that data, I think they had 3,000 data points. If you aim inside the red diving envelope, if you aim inside the red semicircle, your probability of scoring is 0.5. So of those 3,000 data points, around 1,500 of them were successful. Sorry, no, it doesn't quite work, does it? Of those 3,000 data points, let's say 1,000 were inside the red semicircle, and only 500 of those were scored. The other 500 were saved or missed up here. So if you aim inside the diving envelope, your probability of scoring is a half, 0.5. So not bad, but you would like it to be higher. In a penalty, you're meant to score, right? That's the general opinion most people have. So 50-50 odds isn't great. If you aim outside of the diving envelope, so we're talking here, and even the penalties that miss the target, so the ones up here as well, including the ones that miss the goal, if you aim outside, you aim for the unsavable zone, your probability of scoring is 0.8. So you have an 80% chance of scoring based on the historical data of penalties over the last 30 years. If you aim outside of this, you have an 80% chance of scoring. So whilst it's a much more difficult shot, you require much higher skill level to be able to aim successfully for this area. The idea or the data suggests that it's harder, but if you hit that area of the goal, like you're going to score, is what the data is suggesting, because a goalkeeper just cannot reach this area or this area of the net. So first of all, the physics tells you aim outside of the red circle, aim for the unsavable zone. And then even the data supports what our hypothesis or our theory, and says people that aim for this score more often. So that's our first sort of most basic idea here, is aim for the top corners, in short. Now, we can go even further. We can get really into so this was kind of like a statistical analysis and looking a bit at the physics and the modeling of the mechanics of a human and moving. Now we can go even more into the maths because, again, here's a picture of a goal, and then the blue line is my diving envelope. So we want to avoid the blue line because we assume, let's say the goalkeeper is going to save it, just to make it easy. So we want to be away from the blue line because that's the goalkeeper's zone. We want to be away from the crossbar, the yellow one at the top, because obviously that's a miss. And we want to be inside this post. So really, we want to be as far away as possible from the blue line, the yellow line, and the vertical yellow line. So what we can do is, in fact, perfectly fit a circle into that space. So the center of this circle is exactly equal distance from the goalkeeper, from the crossbar, and from the post. And all of these distances, at the very center, all of these distances are equal because each distance is a radius of the circle. The distance from the center to the edge, anywhere on the circle, is the radius, and that always has the same value. So the center of this circle is actually the perfect location to aim your penalty, because we could put so the circle could be this side or it could be over here. Of course, that doesn't really matter. That depends on perhaps which footed, if you're left-footed or right-footed. But you could also aim at the bottom. But the issue with aiming at the bottom is your circle is smaller. So you have to be more accurate. There's like less of an error if you're aiming down here. Whereas if you aim up here, if you aim for the center of the circle, you actually allow yourself quite a large amount of error in your shot. And again, it's in the unsavable zone. So what we want to calculate is what is the center of this circle? Can we figure out how high above the ground and how much inside of the post this magic perfect penalty placement is? And the way we're going to do that is using Pythagoras's theorem. So a squared plus b squared equals c squared, possibly the most famous theorem you've learned at school. So in order to do that, let's add some labels to our diagram. So what we've got here, so the blue line, remember, is the diving envelope. So that's how far the goalkeeper can reach. So we know this. We know the value, capital R for the radius here. We know that value because we know it from the experiments. So we know this. A at the bottom here is going to be the distance from the center to the edge of the post. So half of the width, we're going to label A. I'm going to call the height of the goal B. Again, we know A and we know B because all goals are the same size. And then the radius of our circle, I'm going to call little r. So what we want to know little r. This is the unknown value. We don't yet know what this radius of this circle has to be. But we know capital R. This is a known variable. We know the distance A, half of the width, and we know the height B. So what we can do, as I said, is we can use triangles. Because if I add a black line here, these two touch perfectly right here. The circle is designed so that it perfectly touches this blue semicircle. It's a tangent, if you've heard of that word. So because it's a tangent, what it means is that this distance is actually just going to be capital R to here and then little r to here. So we're going to actually know the length of this side of our triangle. Then we can add a vertical line here, and then we can also add a horizontal line along the bottom. So we've now got a right-angled triangle, and we can figure out the lengths of each of our three sides. So as I said, the diagonal here is capital R plus little r, because you go along the radius of the diving envelope, and then you add on the radius that we don't know. Along the bottom, the total distance is A, but here we are exactly R inside. Because we've gone vertically down from the center of that circle, this distance is R. So the total distance here is A minus R. And then similarly up the side, we can do the same thing. The total distance is B, but from the center here, to the top, we know this has got to be the radius as well. So the distance here is b minus r. So now we have Pythagoras. We've got our two right angle sides, and then we have our hypotenuse. So we know that we have to have a minus r squared, distance along the bottom squared, plus the distance up the side squared equals the square of the diagonal. So this is Pythagoras' theorem. Now, we know A, we know B, and we know capital R. So the unknown variable, think of it as like x when you're trying to solve an equation. The unknown variable here is little r. So let's rearrange the equation. So let's expand out the brackets. We'll get some r squared terms here, r squared, r squared. We'll also get some terms that just have a single r in them. So we expand it out and simplify, we get this equation. So we've now got r squared minus 2r all multiplied by a plus b plus capital R plus a squared plus b squared minus r squared. Now again, the only thing we don't know is little r. So what we have here is something else you'll be familiar with from school. We have a quadratic equation. So all those times, and I used to think this, all those times when you're learning about quadratic equations and the quadratic formula, and you think to yourself, when am I ever going to use that? We're using it here to figure out how to take better penalties and help Ireland qualify for the World Cup. So what we need to do is solve this equation, solve this quadratic equation using our quadratic formula, and that will tell us the answer. So all that's left to do now is add in the numbers, because I've been telling you all along, we know A, we know capital R, and we know B. So A is equal to 3.66 meters. That's half of the width of a goal. We know that B, the height of a goal, is 2.44 meters. And the diving envelope of a goalkeeper is 2.86 meters. So we just take those three values, substitute them into our equation, and what we end up with is this. R squared minus 18r plus 11 is equal to 0. So now it just looks like any quadratic equation that you've seen before, and we can just plug that into the quadratic formula, and we get our answer, which tells us that r is equal to 0.65 meters. So now we know the radius. That means we have to go exactly 0.65 meters inside of the post. And then the height, remember, is going to be b minus r. So that will be 2.44 minus 0.65, which gives us 1.79 meters. So the perfect place to aim your penalty kick, and I hope the Irish team is listening, is 0.65 meters inside the post and 1.79 meters above the ground. Now, the easiest way to do this in practice, I'll try and demonstrate. If this is the post of my goal, if I stand like this in the goal, you want to aim for my face. So if anyone wants to practice this, you stand like this with your arm out. This is about 0.65. And I am about 1.8 tall. So you're aiming for like someone's face there inside the post is the perfect place to put your penalty. And we figured it out using Pythagoras' theorem and using the quadratic equations formula. Okay, so something for you to think about. Here is putting this into practice, shall we say. So I talked about, we've got the unsavable zone. We've got this thing called the diving envelope, where a goalkeeper can reach, and we've just figured out the perfect place to aim a penalty. So looking at these two sets of penalties, so we've got Team A at the top, and this is the location of their 4 penalties, and we've got Team B at the bottom, and the location of their 4 penalties. So I want you to think about and vote in the chat, which team will win? So given this data, Team A versus Team B, this is where their penalties are going. Which team, based on our discussion, which team do you think will win? So I'll give you 20 or 30 seconds, have a quick think about that, and I'll see what you type in the box. Okay, so we've got a vote for Team B. Okay, vote for Team B so far. Another vote for Team B. Good. I think I'm probably inclined to believe you and go with Team B. Another vote for Team B, another vote for Team B. Okay, good, right, perfect. Yeah, everyone spotted the idea here. So I think based on this, Team B looks pretty good, doesn't it? Right? Team A have got, this one's definitely not a great penalty. Team B, this isn't the best penalty, but Team B have got 2 right down here, which seems very sensible. So I think I agree. I think Team B to me looks quite good. Now we can make this a bit easier because I can add the diving envelope now to these charts. So here we can see Team A have got 2 penalties inside the diving envelope. Actually, they've got 3 because this one's right on the edge. So I've counted this as being inside because it's, if the goalkeeper's hand can reach the edge, then they'll be able to save that particular shot. So Team A have got 3 inside the diving envelope, whereas Team B have only got 1. So this one's a bit risky, it's quite close, and this one's quite close as well, but they're just about outside. So based on this, we can actually go one step further because I told you the probability of scoring if you're inside or outside of this semicircle. So what we can do is we can work out the expected number of goals given these shots. So if you put a penalty inside the red semicircle, inside the diving envelope, your probability is 0.5 of scoring. So you can say that you expect to score half of the time. So you can say, well, that's an expected value of 0.5. So if you go 0.5 plus 0.5 plus 0.5 gives me 1.5, and then plus 0.8, because that's a good penalty, so it has a higher expected value. The total there for Team A is going to be 2.3. So their expected number of goals based on this data is 2.3. Now, if we do the same for Team B, we've got 0.8, 0.8, 0.8, so that's 2.4, plus 0.5, that's 2.9. So Team B comes in at 2.9. So if we round these up, because we need to have a whole number, you're expecting Team A to score 2 penalties, and you're expecting Team B to score 3 penalties based on this data and based on our model and our calculations. Now I'm going to color them red and green to show you which teams scored and which teams missed. So Team A scored 2, so that agreed perfectly with our prediction. And Team B actually did even better than we expected. So Team B scored all 4 penalties. Even though we were expecting them to only score 3, again, it's a model, it's a probability. So things are not always true, right? You are making a prediction with some amount of accuracy. So even though our model predicted Team B would win, and it gave us an expected score of 3-2, but the actual score was 4-2. But overall, we got the same result. Our model did agree with what happened here because it told us that Team B would win. And now, finally, as some of you may have realized, this is actually the data from the Ireland-Slovakia penalty shootout and the video I showed you at the beginning. So the Irish team, based on their penalties here at the top, weren't taking the best penalties, unfortunately. So they actually had 2 penalties which were saved, whereas Slovakia were fortunate, but again, they just took better penalties overall, which is perhaps why they were able to win that shootout. But now we know how to take penalties. We can, fingers crossed, the Irish team is listening and they will not lose and will qualify for the World Cup next time around. All right, so that finishes our discussion on football and penalties. And the final part of the talk, as I mentioned, I wanted to talk about marathon world records and how we can use sort of try and predict the future here. So I've just got another little video just to introduce this section for you now. There we go.
Less than 200 meters to go. Eliud Kipchoge, let's keep an eye on the clock. Into the final 20 seconds. Eliud Kipchoge. Whoa! On his shoulder. 140. 140. The unofficial time.
It's his wife.
Eliud Kipchoge storms into the history books in Vienna. 1:59.40, the unofficial time. The first man to run a marathon in under 2 hours.
So that was a little clip from an event that took place the end of last year, so about a year ago now. And that was Eliud Kipchoge, a runner from Kenya. And he was there breaking the 2-hour marathon barrier. So he ran a marathon, which is 26.2 miles or 42 point something kilometers. He ran a marathon in 1 hour, 59 minutes and 40 seconds, which is ridiculous. We will see just how ridiculous that is shortly. Now, this attempt didn't actually count as a world record for various reasons. And I just thought I'd talk you through some of these reasons and also mention some of the amazing technology that was used in this particular event. So the idea was to demonstrate that it was humanly possible to run a marathon in under 2 hours. So again, even though it didn't count as a world record because of various technical rules, Kipchoge just wanted to show it is possible. Look, a human being can do this. So go out there and actually go and do it. He just wanted to be, show it was possible. And then in the hope that someone will go and do it and actually set a real world record. Now, some of the reasons it didn't really count, as I say, first of all, we've got his shoes, these very fun looking shoes. So these are the Nike Vaporfly shoes. These are now the ones he was wearing for the event are now actually banned. You're not allowed to use them in races. And one of the reasons behind this is the inside of the shoe. So here we've got a little diagram showing you what's happening in the sole. And you've got this red thing here, which is a carbon plate. Now, the idea is as you're running, as your foot hits the floor, the carbon plate comes down and then it springs back up and pushes you forwards. So based on their experiments and their testing, Nike have claimed that by having this, wearing these shoes, you will actually run 4% faster in a race because you conserve energy. So as your foot comes down, you then have to use energy to lift it back up and take your next step. So if you have this plate helping to conserve some of that energy, you're using less energy for every step you take. And they've actually got really, really good data that shows, compared to other shoes, if you wear these, you do run about 4% faster. So for once, the manufacturer was correct. You always hear about these claims, but the data does support this. You are able to run 4% faster with these shoes, which is one of the reasons I think why they're now actually not allowed in competitions, because it's seen as, whilst it's not an actual spring, it's a spring-loaded plate. So it's kind of in this sense of fairness and different things. But that's another discussion. But anyway, so he's wearing these shoes, which are a really awesome piece of engineering. Also, things that took part in that event. So they ran in a formation. So the main reason it wasn't a world record is we had this formation. So you can see the orange people here. They were in like a V shape, and then you have Kipchoge right at the back. He's this yellow one. So you have a V shape of pace runners in front of Kipchoge, who's trying to set the record. Because the idea is as you run, the air hits you and then moves around the back of your runners. So you can imagine running forwards, you're like piercing through the air and it flows around the back of all of the runners. So that was what they were doing with that formation. And then also, you can see here the bright green lasers shining off the back of a car. So you have your runners here, and then they've got these lasers shining on the road. And this car was going at exactly 2-hour marathon pace. So the runners knew that as long as they ran exactly on the green laser in front of them, as long as they ran exactly in line with that, they were going to complete the distance in 2 hours. So again, you're not really allowed that for it to count as a world record, for knowing exactly how well you're doing and just following a green line. So why did this event take place? Here is a graph of the men's marathon world record over the last 120 years. It also happens to be my favorite graph. Every mathematician has a favorite graph. If you haven't found yours yet, you will. Or maybe it'll be this one. This graph is just the best. So what this shows is there's a very clear decrease over the last 120 years. We've got going all the way back to the 1900s, 1910, the world record is up near 3 hours. And then this line along the bottom is 2 hours. So the reason we're all so excited as long distance runners about this 2-hour barrier is we're getting so close to hitting 2 hours. So your final task of this morning's talk, I want you to look at this graph and then sort of, as much as you can in your head, try and extend into the future and predict when the data will cross through this line at the bottom. Okay, so each of these lines, so this one's 2020, this is 2030, this is 2040 and 2050. So you've got 4 categories to vote for. We've got, do you think it will go below this line before 2025? Will it be between 2026, 2030? That's B. Option C, 2031 to 2035. And option D, 2036 plus. So based on the graph, when do you think this will continue down and go through? So we're trying to make a prediction. We're trying to use data from historical data and try to make some kind of prediction into the future. And we do this a lot in maths, actually, like a lot. You do this a lot with scientific data. You do this a lot, particularly in economics, in banking and trading, and all investors will try to predict trends in the future based on what's happened in the past. So I'm seeing almost everyone's voted for B. Okay, so we've gone for, in general, we're thinking then 2026 to 2030. Okay, so what we can, of course, do, being mathematicians, is we can do a line of best fit. So a line of best fit can be any shape. In fact, you're maybe used to straight lines, but they can be any shape. So what I'm going to do here is draw a cubic, an x cubed graph. Okay, so y is x cubed plus an x squared, blah, blah, blah. So it's a cubic graph because it's a bit more curved, and clearly our data has a little bit of a curve in it. So I can just fit this line using what we call least squares regression, which is just a fancy way of saying I want the line to be as close as possible to every point. That's the idea. So if I do that, it looks like the red line on the screen. And this one actually crosses somewhere down. It's definitely past 2030. I've called it about 2035. So based on an x cubed graph trying to fit this data, we get this red line is our best fit. And that gives me a prediction of 2035. Now, the question you ask yourself as a mathematician at this point, as in fact as any scientist, is it correct to use all of the data here? Because do you think, and this is completely up to personal preference, do you think that the world record in 1910 has any effect on the world record today, given how different long distance running was 100 years ago? For example, people didn't have special running shoes. You didn't train every day. You didn't have a personal trainer or a coach. Now they have nutritionists. There are all kinds of developments that have happened in the last 20 years, mainly, to make long distance running. It's now a professional sport. In the 1990s, it wasn't. You had a real job and you trained when you had spare time. So anything from like 1990 and earlier, I would argue, from my personal opinion as a mathematician scientist, doesn't really matter. And so if you actually go back to the original graph and focus on the last 20 years only, because as I've said, there's been this massive change in making runners are now professional athletes, which never used to happen. So because of that, you see, if I zoom in on the last 20 years, that's what the data looks like for the last 20 years. Now that to me looks exactly like a straight line. So now we can just plot a y equals x graph and do a line of best fit in the same way as we did before. So we'll do that prediction. And now we get an earlier prediction of 2027. So 8 years earlier than the prediction with all of the data. Now, of course, and this would agree with everyone's votes. So perhaps this is what you were all thinking when you were voting for section B. Now, I can't tell you which one is correct. I can't actually predict the future. But this is the kind of way you would analyze a problem like this. And this could be any data. I've just picked marathon world records. But with any set of data, you have to think carefully about what are your assumptions and whether or not you need to use all parts of that data. And if you exclude things, as long as you give a reason why, then that's fine, because somebody reading your work can either agree with you or disagree with you, but they need to know what you've done in the first place. Okay, so we can go even further, which of course I had to do being a mathematician. Full statistical model. So this is like the most advanced statistics you can do on this. This is the same graph, same data points. We've got all of these predictions. I'm just going to highlight a few interesting things. So our first prediction was 2035. Our second prediction was 2027. So the one in the middle, based on the full statistical model, gives me a prediction of 2032 for the record to go below 2 hours. And it even assigns a probability. So it says here there's a 1 in 10 chance. So there's a 10% probability that by the year 2032, the world record will be less than 2 hours. So, and as I said, that's a full statistical model. I'm not going to talk through the details because it's quite advanced. But the really interesting thing we can do with this is you'll notice these curves, they go flat. So our curves, in particular the straight line one, that would keep decreasing forever, which of course is nonsense. The world record will never be 1 second, ever. No matter what happens, and you can hold me to that. No one will ever run a marathon in 1 second. So it's got to flatten at some point. So the question then becomes, what is that limit? What is the fastest you will ever run a marathon as a human being? And you can just continue these lines, and when they go flat, that will be your prediction of how fast you can run the marathon. So here, the limit for men is 1 hour, 58 and 5 seconds. So this full statistical model says the fastest any male athlete will run a marathon is 1 hour, 58. Now you can do the same for the female world record over a marathon. Now here, most of these lines, some of them just about go below 2 hours. So there's a line here that says by the year 2030, you would expect the female world record to be below 2 hours with a 1 in 200 chance. So it's definitely possible. It just seems much, much more unlikely than the male one being less than 2 hours. And that's just based on the differences in those world records. Now here, the female limit is predicted to in fact be 2 hours and 5 minutes. So that's seen to be the most likely fastest ever time for a female athlete to run a marathon. Now, very final thing, just to sum up, I told you I would emphasize just how difficult it is to run a 2 hour marathon. So what I've just got here are various distances that you would see in typical races or Olympic events. I've got the men's world record and then the women's world record. And what we can figure out is if you're running a marathon, 42 kilometers in 2 hours, that's 42,000 meters in 120 minutes. You can then divide the distance by the time and figure out what is your average speed across the entire marathon. And then you can work out, well, how fast, if I'm running a 2 hour marathon, how fast do I have to run every 100 meters? You can do this calculation. And I've done it for you. The answer is you have to run 100 meters in 17 seconds, which I think is pretty doable. If you're athletic, if you play sport, you can almost certainly do this. Run 100 meters in 17 seconds. No, it's definitely not impossible, shall we say. Now, could you do it 422 times in a row at the exact same speed without stopping or having a break? Probably not. So you've got to run the 100 meters in 17 seconds and you've got to do it 422 times. Now you can figure this out for the other distances. And as I fill this table in, I want you to think in your head, at which point would you fail to do one of these times? So at the moment, you might be thinking, I can't run the 100 meters in 17 seconds. And that's fine. So you're already like out. So you've you're already cannot do the first 100 meters of 42,000 meters that you need to do at this pace. And that's fine, because this is ridiculous. This is insane to run this quick for this length of time. So the next one, the 200 meters. So if you're still in, the 200 meters, you've got to do in 34 seconds. Again, you've obviously got to do it 211 times, but let's just pretend we're just going to do it once. So I know that I've actually timed myself on these. So I can do the 100, I can do the 200. The next one's really, really hard. So I'll be impressed if anyone is in on the next one. So you've got to run 400 meters, one lap of a running track in 1 minute and 8 seconds. That's tough. That's very tough. You need to basically be a 400-meter runner, I think, to be able to do that. So I can just about do that one. I think I can do it in 1 minute 5 is my personal best. So I can just about do the 400 meters. But that's literally less than 1% of the pace that these athletes are running for 2 hours. It is insane. I fail on the next one, so I'll be super impressed if anyone's still going at this point. I definitely cannot do the 800 meters in 2 minutes 16. That's incredibly quick. The world record is only 140 or 153. Like, that is insanely fast. Then the other interesting one I've put here, 5K. So when you get to the 5 kilometer mark, you've got to run 5 kilometers at the same pace as the women's world record. But you're not just doing it once, you're doing it 8 times in a row. Then, of course, you've got to do the half marathon in an hour, which is faster than the women's world record, which is insane. And then last thing, final video to close. So we've got here 200 meters in 34 seconds. So at the Chicago Marathon 2 years ago, they actually set up a treadmill for people to run on, and the treadmill was running and programmed to be running 200 meters in 34 seconds. So there's a great little video of people trying to do this.
Trying to survive something like that for 2 hours would be almost impossible. It's unreal that somebody did that.
Right, that's the end of my talk. So thank you, and happy to take any questions you have.
Okay, that was great. Thanks.
I'm just fixing my headphones. We'll be with you all in a second. Okay, right. I think I can hopefully now hear you all again. Okay, perfect. Right, I'm back. Yeah, so any questions about penalties, about marathon running, about maths in general, about university, anything you want, I'll happily have a go. About me, if you really want to know more about me, happy to chat about that. Really, anything at all. No problems. Also, if anyone claims they can do the 800 meters in less than 2 minutes and 16 seconds, if you film yourself doing it and like send that video, I will be so impressed. I'll give you a shout out to be like, this is amazing. So that could be your sports challenge for Maths Week. Can anyone run the 800 meters? Oh, actually, you know what? Let's just say the 400. If anyone can do the 400 in 1 minute and 8 seconds, less than that. That is really, really hard. And then, you just have to do it another 200 times or something. No, 100 times, wouldn't it? Another 100 times. Oh, we have a challenger for that. Here's a 400. Okay, awesome. Yeah, I would love to see that. Genuinely, if you want to have a go at trying to do the challenge, do let me know. That would be awesome to see. I think that everyone's on mute, are they? Great question. I love it. I mean, for me, first of all, getting to be a mathematician is something I think I've always wanted to do. Like from when I studied maths at sort of for me doing A levels. So when I was sort of 16 to 18, I did double maths and just absolutely loved it. Thought it was the best thing ever. And then wanted to study at university, and then been fortunate enough to basically just keep studying it. So the mathematician aspect is amazing. Like just every day being able to work through interesting problems. So like the stuff I've talked about here, the thing with the penalties, I really like football, and I thought from the sort of motivation for me was, why are England so bad at penalties? So I decided to do a bit more research into it, and then came up with what I think is a reasonably simple explanation involving Pythagoras and quadratic equations, which you've all studied at school, which sort of give you some insight. So the maths aspect for me is brilliant. Being at Oxford obviously is also great. I won't, I wouldn't be here if I didn't really enjoy it. Something that I think a lot of people are apprehensive about, and even I was a little bit when I was applying. So I studied my degree in Oxford, but when I was applying, nobody else in my family had been to university. Nobody else from my school had ever gone to Oxford or Cambridge or any sort of top ranked university. And I did feel, I wouldn't say too much, it was mainly more from my parents, but there was some kind of like apprehension of like, will you fit in? And is it all very like traditional and posh and various things? Because you sort of has that stereotype. And it's obviously there's lots of traditions, right? Like yesterday evening, I definitely went to a hall in a gown and felt like I was in Harry Potter. But everyone is also kind of in the same boat. I think for like 90%, if not more, of people here, it's all as crazy and weird as it looks to the outsiders. Like the fact that I have to wear a gown to eat my dinner is completely ridiculous. But I kind of love it because it's part of the tradition, and it's part of what makes these very old universities. It's part of what makes them what they are. But I would say everyone's really friendly. That there isn't a typical student. There isn't even like a typical person. I think the stereotypes exist, but they're very much based on old and out of date views. I know, for example, this year the university, as an example, has admitted more state school students than ever before. I think it's now way over like maybe 60-70% of the students come from state schools, for example, which goes against the stereotype. So I think it's very, very important to not have those preconceptions in your head about any sort of prestigious university. But as I say, sort of for me, I absolutely love it here, and the fact that I'm able to just spend my time doing maths and doing things that I love is obviously amazing. Yeah, for the 1 minute and 8 seconds. So yes and no. So I run marathons myself. So I'm training for those. So for example, I did my most recent one was a year ago. I did the Chicago Marathon in 3 hours and 11 minutes, which is personal best. So I was so far off 2 hours, obviously, but I was a good hour and 11 minutes, a good 50-60% on top of the world record time. But yeah, so I do a lot of I do enjoy, as I said, this is why I talked about football and long distance running, because they are my 2 favorite sports. They're my 2 favorite hobbies. So I guess I had that training, but in terms of like trying to run it, I didn't. Beyond that, I had a few goes and eventually managed to do it in 65 seconds. So I think anyone, as I say, anyone who like does a decent amount of sport, if you like play competitively for your school or at county level or anything like that, you're probably got a decent level of fitness to at least give it a shot and see if you can manage the 400 in 65 seconds. The 800 in 2 minutes 16, you would absolutely have to be a trained 800-meter runner to get close to that. That's the one that's, yeah, you've got to full on be an 800 meters runner if you're going to do that. But the 400 one, I think, again, if you play a lot of sport, you've got a chance. The 200 one, again, similar. The 100 and 200 are probably the most approachable. And then the 400 is where it starts to get quite tough. Brilliant. Yes, let's get this on social media. Hashtag outrun Tom for Last Week Island. Maybe, I tell you what, maybe we should try and get 422 people to do the 100 meters faster than 17 seconds. And then add them all together and we've got a marathon world record. Yeah, we've got an aggregate marathon world record. So we need 422 of you to do the 100 meters in less than 17 seconds. Or 211 to do the 234, etc. We can just add everyone's times together. Oh, that's a great question. Yeah, 100%. So if I was here, I reckon 10 years ago, the answer would be no. Today, absolutely. So I think the example that sticks in my head the most with this would be the Leicester. So Leicester City won the Premier League in 2016, and they were previously sort of mid to lower league team, and just out of nowhere they just won the league that season. And one of the main reasons, there were several reasons, no doubt, but one of the main things, and I think he actually won Player of the Year, was one of their midfielders called N'Golo Kante. Now, he's a French midfielder, and Leicester signed him based on the advice of a group of data scientists, mathematicians, statisticians, etc. It was very much not a traditional transfer in the sense of normally you would have scouts, they go to watch players and sort of get a feel qualitatively as to how that player plays and assess different things. But N'Golo Kante was one of the first examples of a player that was signed purely based on data. Because what they spotted, he was playing in the French second division, and what they spotted was his statistics for interceptions. So that means basically kind of, your opponents are passing the ball and you step in and intercept the pass and win possession back for your team. His statistics for interceptions were astronomically higher than any other player in any other league around the world. So he was like an anomaly. It sort of looked like it was a particular piece of data that really stood out. And based on that, they actually then signed him for a reasonable fee because he was coming from a lower league team, and he turned into the player of the season. And, was one of the key things why they won the league. And obviously he's now playing for France, playing for Chelsea, as one of the best midfield players in the world in that position. So I think that was perhaps, I would argue, possibly the catalyst to then make all of the other teams really take this stuff seriously. So most teams now, especially the big teams in all of the leagues around Europe, now actually have mathematicians, statisticians, data scientists working for them. And it's their job to track player stats, either players on their own team to identify, is this player running enough? Where positionally are they on the pitch? Are they following tactics? They now have all of this data that's used to help the coach and the manager alongside the team. So yeah, it's a really nice sort of career path for mathematicians, which has recently opened up. Yes. Thank you very much. Cheers, everyone. Bye-bye.